Okay, so just to finish up fusion, I just wrote down here two different examples of fusion reaction. So the first one, it's two hydrogen 2s being fused together, and you get out a hydrogen 3 and a regular hydrogen, and then 4 mega electron volts of energy. And then another possibility would be a hydrogen 2 and a hydrogen 3 isotope, giving you helium and a neutron and 17.6 mega electron volts of energy. Okay, the reason I wanted to come back to it was to tell you like how you would get these. So what will happen will be you'll be told the mass of the two reactants, and you'll be told the mass of what comes out. And so if you add these together, the two reactants together, and you add the two products together, the difference between them will be the mass that's lost. And of course, the mass that's lost is then not, it isn't really lost, it's converted into energy. So if you're told them in atomic mass units, in U's, then you'll take your atomic mass units and you'll change it into mega electron volts, right? By doing 931.48 mega electron volts per U to get how much energy. If you were told it in kilograms, then you would use the E equals mc squared. And there's no line there. I don't know what my hand was doing. It's pretty good when you get that equation wrong. You do E equals mc squared. It just doesn't want to work. If it's in kilograms, okay? So if it's in atomic mass units, then it's the delta mu, and this will be E equals the delta m times 9.81, but if it's kilograms, then it's times the speed of light squared. Okay, so you can figure out how much energy would be given off in each fusion reaction, but you'd have to be given the masses of the reactants and the products. And I wouldn't expect you to know, hey, if I put two H2s together, I'm going to get an H3 and a regular hydrogen. No, like you'll be told that in the question. So that like you'd never be expected at this point in your career to be able to predict what's going to come out. And even in the other nuclear reactions, like you'd have to be told one of the two on the product side of what comes off, and then you could figure out the other. So I could say here, hydrogen 2 and a hydrogen 3 are fused together and a neutron's released, and then you could figure out that this would have to be a helium, would have to be the thing that was formed, right? But I wouldn't expect you to know that a helium and a neutron are formed. Does that make sense? I hope so. All right, so all we have left in the unit, and we'll finish it up tomorrow, we'll be talking about antimatter, and maybe I'll talk about antimatter right now because we have some time, and then tomorrow that'll leave us subatomic particles. All right, because I've already mentioned antimatter a few times. So you will often hear us talk about particles and their antiparticles, which is exactly the same thing as saying matter and antimatter. So what we now know, but for a while was proposed, is that every particle has an antiparticle. Now, the antiparticles or the antimatter, we've really only seen in those artificial transmutations, like they've been given off, with the exception of the antineutrino, I guess. The antiparticle or the antimatter is identical in every way to its particle in size, but it's opposite in nature. So an electron and a positron have exactly the same mass. It's just the electron is negative and the positron is positive. The proton and the antiproton, it doesn't have a fancy name because by then we knew about antimatters, have the same mass, but a proton is positive and an antiproton is negative. Originally, people, the unphysiced among us, might think the proton and the electron are antiparticles of each other, but they're not because their mass is different. So even though they have opposite charge, they have a different mass. Okay? Now for a neutron and the antineutron, it can't be opposite charge because a neutron and an antineutron are neutral, so it's opposite spin for them. Okay? Neutrino and an antineutrino would be the same. It would be the opposite spin as opposed to charge. Okay, now the coolest thing in the world happens when an antiparticle and its particle come together. And it's the reason why you don't find antiparticles in the world. Antiparticles do not last long, do not exist long in the presence of matter. Because as soon as an antiparticle encounters its particle, they annihilate each other. They come together and they turn, their masses vanish and they turn into pure energy. So it's called if I could spell it, annihilation. Okay, now when I was a kid on the school bus, there used to be this little guy that was kind of obnoxious, and so of course that meant some older guys would pick on him, and he was quite the bright little guy, and he would look at them and he would say, "I'm going to annihilate you." Probably not a good thing to do, because when you annihilate someone, you disappear too. So both like if it's an electron and a positron that come together, they both disappear and their mass turns into energy using the E equals mc squared. It's why when we're doing all of the stuff to try to find, new subatomic particles, like when we speed a particle through a particle accelerator and then slam it into a sample, we do it in a vacuum. Because if we didn't, things would be annihilated before we even got to find out what they were. So everything's always done in a vacuum. So annihilation happens for all particle-antiparticle pairs. The electron is the one that gets the cool name for its antiparticle. And it was, again, because when it was discovered, we didn't know what it was. Now, you might think that these are the only 4 particles, but you need to come back for the next video to discover that's not true. All right.